We're on page number 102. And on 102, we're still compounding interest, but we're doing a concept called compounding continuously. And I want you to notice that that fantastic letter E has found its way into this formula, which means that we're going to probably be using natural logs in this section. Now, there's a lot less to look at here. The ending amount, the principal, the interest rate as a decimal, and time. So this should be kind of easier, right? We're looking for an interest rate. When you see this word that tells you to use this formula, and we know that we're starting with 5 grand and we want it to be doubled in 12 years. So double is 10 grand, starting with 5 grand, E, we're looking for an interest rate and we know we have 12 years. So this is what things look like. I am going to pick away at my power and try to get it as basic as I can. So now I'm sitting here, I'm actually going to put the 12 up front with the power, really. I have E raised to the power of 12R equals 2. I'm going to change this to log form. So natural log of E of 2 equals 12R. That's what it looks like. When you have R multiplied by 12, I can get R alone by dividing both sides by 12. So what I'm putting in my calculator is going to be this little sweetheart. Remember that natural log has an E in the base spot no matter what. So when I put this in the calculator, I actually can just write it like this, natural log of E over 12. So bringing up my calculator, natural log, I'm actually typing it out because it's much easier for me. Natural log of 2 over 12. 2 divided by 12 gives me 0.0577, 0.0578 if we want to make this easier and proper. So that tells me that my interest rate is 5.78%. Okay, so what if I am looking for an unknown in a different spot? I have $2,000 invested. It pays 5% annual interest compounded continuously, and they want it to double. Doubling is 4 grand. I start off with 2 grand. E, now I have a rate and I'm looking for time. I'm going to let you finish this out because the process is almost exactly like what we just did. And you want to definitely get good at this and understand that the difference between that last formula and this formula is how many times it's compounded. If they give you a number, then you know that you use the compound, the simple formula. And if it's continuously, you use the formula that has E. That brings us to page 103. On page 103, we are solving log equations, and the steps are at the beginning now. So you always want to start by isolating the log. I'm looking at these very first 2 examples, and the log is isolated, but sometimes it's not. So if there was a deal where I had to add something to both sides or multiply or divide both sides by something, then that would be the next thing. I'm going to go ahead and change this to exponential form. There's nothing written in the base spot, so I can assume it's 10. 10 raised to the power of 4 equals x plus 4. 1, 2, 3, 4. All I have to do is get rid of that 4 by subtracting both sides. 9,996 equals x. Not terrible, right? If I was going to change this to exponential form, 10 squared equals x plus 20. Where did that 10 come from? It was right here. 100 equals x plus 20. If I subtract 20 from both sides, x is 80. Okay, so let's take a look at page 104 because we're going to do a practical application of solving log equations. This log equation actually represents ways to measure earthquakes. And the unknowns here could be the magnitude, it could be the intensity. That's what M is. This is what I is. S stands for a standard quake, which we are just going to always, in this example, replace S with 10 raised to the power of negative 4. So actually, this formula is like this. And so there's two unknowns in the formula, M or I. So this first one says, if the intensity is 40,000 centimeters, what is the magnitude? All I have to do is plug in 40,000 where there is an I for intensity and throw this in a calculator. 40,000 divided by 10 to the power of negative 4, all tucked into a log. So I'm going to bring a browser up and let's look at log. I'm going to spell it out because it's much easier. Log, open parenthesis, 40,000 divided by 10 to the power of negative 4. 8.6 is the magnitude. 8.6. So I'm going to go ahead and write 8.6. And that sounds about right. It sounds like a terrible, terrible size. It's terrible. This next question is a little different because they give you the magnitude and ask you for the intensity. So when I plug my numbers in, it's going to look like 6.5 equals the log of intensity, I, over 10 to the power of negative 4. So because I need to dig something out from under a log, I'm going to have to go ahead and change this to an exponential equation. So I'm actually going to put my power on the left. So I'm going to make it look like this. And I am going to ditch that word log. I'm going to say 10 to the power of 6.5 equals I over 10 to the negative 4. And all I have to do is multiply both sides by 10 to the negative 4. And if you remember when we are multiplying powers that have the same base, you just add the exponents. So my intensity is going to be 10 raised to the power of 2.5. And this I can't do in my head, so I'm going to throw this in a calculator. I got 316. Now this is an exponential equation. So remember that exponential equations can be very, very small and all of a sudden get very, very big. That's why you would get a 40,000 intensity here and a much smaller intensity there. You can't really look at this like you would look at something that's linear. There is a practice one on page 105 that you're going to do when you get a moment. So we're going to the bottom of page 105. We are solving these log equations. Remember that you can do whatever you want as long as you do it to both sides. So if I had something like x equals 5, I could take the log of both sides if I wanted to, but why would I do that? Except I'm wanting you to notice that if you can take the log of both sides, you can take the unlog of both sides. This is x equals 5. Next one, natural log of t equals 3. We're just trying to figure out what t is. Remember that there is a base of e for natural logs. So if I change this, oh, no, thank you. Looks delicious though. I make e big, 3 and t, change spots over the equal sign. And then I just have to put in my calculator e to the third power. Remember the e is just a number, just like pi. So I'm going to put in my calculator e raised to the power of 3. And that's going to give me 20.0855. We are going to round that to 0.086. C, I've been telling you all along, when you are solving log equations, you have to isolate your log. If you're solving exponential equations, you have to isolate your power. But in this case, I had to subtract 7 from both sides. So then I could go to the next step, which is to convert this to exponential form. 10 to the 12th power equals 2x. I'm going to divide both sides by 2. This is crazy big. And actually, it's not the 12th power because I forgot. I didn't even subtract 7 from that side. Let's go back here. 12 minus 7 is 5. Now I have 10 to the 5th power equals 2x. To get x alone, I would divide by 2. That would mean that x equals 1, 2, 3, 4, 5. This is 100,000 divided by 2. That's 500,000. That's 500. That's 50,000 because I'm so good at math. 50,000. I'm good at math and have great handwriting. Here's a few other examples that I want you to do that are very similar to the 3 that we just did, and then you can log in and look at my notes to see if you did that correctly, but we are going to go down here to the last 4 questions. These questions all involve having the knowledge of how to condense a log. So we were expanding and condensing logs using properties. Remember, you can do that. Like, for instance, A could be written as log base 6 of x times 2x equals 2. If I was really smart about this, I would write it this way. And then I can change this to exponential form. 6 squared is 36. If I divide both sides by 2, 36 cut in half is 18. So I have x squared equals 18. I would square root the both sides and get plus or minus square root of 18. Or I could say plus or minus 3 radical 2, that is the square root of 18 simplified. So you can see that B is like a similar situation. If I were to take these logs, write them as a single log, I would have to multiply 2x and x minus 4. But I want you to notice that this is equal to 1. And we have this thing about if something is equal to 1. But let's just keep going through this and seeing how we do. 10, right here. 10 raised to the power of 1 equals 2x squared minus 8x. I just distributed. And this is so fun. We have a situation where we actually are going to end up with a quadratic. If I subtract 10 from both sides, I have this equal to 0. And we have to go through all of the process that we would normally go through to see if we can factor this to figure out what the solution is. So we're probably going to have 2 solutions. What if you can't factor it? Remember, you can go straight to the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Factored, this is what you're going to get. Yeah, I went through all of this right off of camera. These are the 2 factors. So one of my solutions is going to be 5. That's for the second factor. The other one is going to be negative 1 because I'm looking for numbers that will make this equal to 0 or this. So the 2 solutions for B is x equals 5 or x equals negative 1. I'm just going to circle these up here because I'm running out of room. Let's look at C. Log base 2 of 3x squared over x equals 5. I actually could simplify what's going on in here. This is equal to 3x. I can cancel an x from the top and the bottom. 2 to the 5th power equals 3x. I went ahead and I went to putting this in exponential form. 2 to the 5th power is 2 times 2 times 2 times 2 times 2. It's 32 divided by 3x. Well, we're going to divide by 3, equal to 3x. So I'm going to leave this in fraction form, and WebAssign will also allow you to do that. D is the last one, log base 2. We would be multiplying these equal to 1. 2 to the 1st power equals this. That's what that looks like. And we won't be able to solve this unless we put this into quadratic form over here, and then we subtract 2 from both sides. So this would be x squared plus 9x plus 20, subtract 2, x squared plus 9x plus 18, 1 and 18, 2 and 9, 3 and 6, 3 and 6, x plus 3, x plus 6. 2 solutions for this will be negative 3 and negative 6.